Okay, here we are, question 5 on the 2019 AS paper 1 from AQA. Again, this is so that you guys can do a little bit of dirt work. You can see one approach, one method of doing these questions. So here we've got a 100 centimeter ruler that is suspended from two force meters, A and B. They are attached to the ruler 12 centimeters from each end. Their supports are adjusted to make A and B vertical to the ruler and to make the ruler horizontal. So whenever everything is square, this is a practical that pretty common to do in class, kind of finicky to set up, but you're not being asked to set it up and do it. You're just being asked to do some math with it. So here it says we've got a uniform ruler and it weighs 1.12 newtons. Determine the reading on A. Well, A and B are the same distance from the edge. It's a uniform ruler. That means that they're the same distance from the center of mass, because the center of mass is going to be directly in the middle of our ruler. And so you just have to divide the weight by 2, because A and B are going to be equal. Everything else is equal about it, so it should be equal. And here the ruler is so 1.12 divided by 2. 1.12 divided by 2, and that equals 0.56 newtons. Very easy. No need to do any moments or anything like that. Just a little bit of logic. Realize that everything is equal, so divide by 2. Is this a couple? No. No. The forces are not acting in opposite directions. So in order for it to be a couple, the forces need to be equal and opposite and acting along the same line of action, basically. So you should be able to move them on top of one of each other with just a simple transformation. And here you can't do that. They're acting in the same direction, so they're not actually going to spin the ruler. So no couple. I'm just going to quickly check my mark scheme here and see if they want anything extra from that. They do want a mention of what a couple is, so it's two equal forces acting in opposite directions. So you should define a couple before doing that. So I would probably only get 1 mark from my written answer there. Well, if they could read it. So here, oh, this is fun. Okay, so this is basically simultaneous equations. We got to look at moments and all that wonderful all that all that wonderful math. So I'm gonna label my center of mass here, and I'm gonna put the weight from my ruler there. We know that's 1.12. So I am going to take, where do I want to take my moments about? All right, I'm going to take my moments about A. So I'm going to take my moments about A. That means that for my moments, I'm eliminating the force A. Okay, so I'm going to balance my moments about A. So I'm going to have W times D plus 1.12. Now this distance is 50 minus 12, so 38 centimeters. It's fine to leave it in centimeters because at the end of the day, it just means that D will be calculated in centimeters. W will still show up in newtons. And that is equal to 0.62. And this distance here is 38 plus 38 is 76 centimeters. So W times D is equal to times, what is it? Oops. .62 minus 1.12 times 0.38. So W times D is 46.69. No, I wouldn't use that many significant figures in an answer, but I'm not at my answer yet. So now what we have to look at is that all the forces are balanced because we're in equilibrium. So that means all the upward forces and all the downward forces add up. So W plus 1.12 is equal to 0.82 plus 0.62. So W is equal to 0.82 plus 0.62 minus 1.12, 0.32. So that's W, 0.32. So D is then going to be 46.69 divided by 0.32. Well, that ain't right. Must have made a mistake here somewhere. Yeah, something's not right there. W times D is wrong. Oh, that's why. If you're going to deal with centimeters, stay in centimeters. 4.56. That looks reasonable. Okay, and then that changes to... That's a reasonable answer. And correct number of significant figures, 0.14 meters, because I want the answer in meters. Okay. Yeah. So this is just a really, really good example of one, a sanity check. So I could look at that and my answer with 148 centimeters, it can't be 148 centimeters away. It would be silly for me to put that as my answer. Um, and there, remember, I specifically said, hey, you can stay in centimeters. You don't have to worry about it. Your answer will just be in centimeters. And then I did half of my calculations in centimeters and half my calculations in meters. And, well, I made a mistake. And not the first time I've made that kind of mistake. Probably not the last time I'll make that kind of mistake. Fortunately, this is really low stakes. But let's say I was doing a job for, I don't know, engineering, trying to work out something on a bridge, and I got an answer like that. You, big time problems. So let's just be careful about what we're putting in. We just you need to be consistent. With units, you need to pay attention and always do those little sanity checks. Okay. Realistically, I probably should have looked at W times D and noticed that it was 100 times too big, but or 10 times too big, but I wasn't paying enough attention. Okay, so 5.4. Student sets up the same apparatus as shown in figure 9. She suspends the mass in the same position on the ruler. Okay, so sorry about that. Okay, so the supports have been made vertical, but the ruler has not been made horizontal. Discuss whether the readings will be different. They should be different. Different. As the horizontal distance between W and A and B is less. Okay, and the reason that it's less, well, it is less because it's now at an angle. Okay, so because it's at an angle, it will be less. The amount that it will be less um, will vary, but now we're gonna have a different value. Oh man, well, I was wrong about that one. Oh, I don't know why. I've done this math in class for you guys before. Yeah, the distances actually, because they're affected by the same factor, which is cos theta, they're going to be the same readings. Obviously, they would add up to the same amount, but they would be the same readings as before, simply because they're all everything is just got a factor of cos theta in there. But everything has the factor of cos theta in there, not just one value or two values. So it actually doesn't matter Um, so just in case somebody comes and looks at this. So again, don't be afraid to be wrong. Um, if you're wrong, just be open to the fact that you're wrong and that you can make the improvement. So, um, ugh. Well, that's question 5. You can see I made a few big mistakes on this one, which actually, I mean, it's not that surprising. I mean, I see students, they make mistakes on this is one of the harder topics in AS moments. They do tend to not like this one as much. This one and momentum tend to cause a lot of problems. But we're almost done. Just one more question to go.